So having now iterated through all of our algorithm design paradigms and noticing that none of them seem to work very well for computing the maximum weight independent set of a path graph, we're going to develop some ideas for a new paradigm. And the key approach in this new paradigm is to first reason about the structure of an optimal solution. And what I mean by this is we're going to seek out statements of the following form. The optimal solution, whatever it may be, has to possess a certain form. It has to have been built up from an optimal solution to a subproblem in a prescribed way. So in fact, in much of our discussion of both divide and conquer and greedy algorithms, this kind of reasoning was implicit. With dynamic programming, we're going to make it systematic. For example, implicit in the correctness of many a divide and conquer algorithm is the fact that an optimal solution to the whole problem has to be expressible, has to be constructible in a prescribed way from solutions to smaller subproblems. So what's the motivation for doing this thought experiment, trying to understand what the optimal solution could possibly look like? Well, the plan is we're going to narrow the possible candidates for the optimal solution down to a relatively small set of candidates. With a small set, we can get away with brute force search to pick the best one. So one lesson you learn once you get good at dynamic programming is that it's not at all circular to reason about the very object that you're trying to compute. Remember, the goal here is to devise an algorithm to compute an optimal solution. And now I'm telling you to do a thought experiment as if you had already computed it, as if I had handed it to you on a silver platter. But that kind of daydreaming can be very productive in thinking, hey, what if I did have an optimal solution? What could I say about it? What would it look like? Observations of that form can actually light up a trail to the computation of that exact object. And we'll see that in the next couple of videos. All right, so that's enough lofty philosophy for now. Let's get concrete. Okay, so we've got this path graph. The vertices have weights. We want the max weight independent set. Let's again do this thought experiment. What if someone handed to us, what can we say about its structure? We'll be using the following notation when we reason about this maximum weight independent set. S denotes the vertices in that optimal solution in that max weight independent set. And we're going to let V sub n denote the rightmost, the final vertex of the input graph. So here's a content-free statement. This last vertex of the path, V sub n, either it's an S or it isn't. So that's going to give us two cases when we reason about the optimal solution. Let's start with the case where Vn is excluded from the optimal solution, capital S. So let's let G prime denote the path graph you get by plucking off Vn, plucking off the rightmost vertex from the original graph G. So let's make a couple of trivial observations. So first of all, this set capital S, it's an independent set in G. It doesn't include the last vertex. So we can regard this set S equally well as an independent set of the smaller graph G prime. If it didn't contain consecutive vertices in G, nor does it in G prime. But actually we can say more. Not only is S any old independent set in G prime, it has to be an optimal, that is maximum weight independent set in G prime. Why? Well, if there was something better than S in G prime, we could take that exact same independent set S star, regard it as an independent set in G, and of course it would still be better than S in G. But that contradicts our assumption that S was a max weight independent set in G. So summarizing, if the max weight independent set S of the original path graph G does not include the rightmost vertex, it can be very simply described in terms of an optimal solution to a smaller subproblem. It literally is a max weight independent set of G prime, the path graph with one fewer vertex. All right, so case 1 is a warm-up for case 2, which is similar but slightly more complicated. Now let's assume that the max weight independent set S does in fact use the rightmost vertex Vn. Now, by the definition of an independent set, no two consecutive, no two adjacent vertices can be chosen. So by virtue of choosing V sub n, the rightmost vertex, S in this case absolutely cannot include the penultimate vertex V sub n minus 1. So we're going to note by G double prime the path you get from G by plucking off both of the rightmost two vertices. So now let's do our best to mimic the argument in case 1. In case 1, we said, well, S has to also be an independent set of G prime. Now here that doesn't make sense, right? Here S contains the last vertex, so we can't talk about it even being a subset of any smaller graph. However, if we think about S except for the last vertex V sub n, S with Vn removed is an independent set, in fact, of G double prime, because remember, S can't contain the second to last vertex. And once again, just like in case 1, we can say something stronger. S with Vn removed is not any old independent set of G double prime. It actually must be an optimal one. It must have maximum possible weight. The reasoning is similar. Suppose S with Vn removed was not the best possible independent set in G double prime. Then there's something else, call it S star, which is even better, has even bigger weight. How do we get a contradiction? Well, if we just add Vn to this even bigger independent set S star that lies in G double prime, we get a bona fide independent set of the entire graph G with overall weight even bigger than that of S. But that contradicts the optimality of S. So, for example, you could imagine that this purported optimal solution, capital S, had total weight 1100 in 2 parts. It had 1000 weights coming from vertices in G double prime, but it also had V sub n, which had weight 100 on its own. And so now in the contradiction, you say, well, suppose there was an independent set that had even more than 1000 weight just in G double prime, say 1050. Well, then we just add this last vertex V sub n to that. We get an independent set with weight 1150 in the original graph G. But that contradicts the fact that S was supposed to be optimal with weight merely 1100. So notice that the reason we're using the graph G double prime in this argument, it's to make sure that no matter what S star is, no matter what this independent set of G double prime is, we can just add Vn to it blithely and not worry about feasibility. Right? So the rightmost vertex S star could possibly possess is the third to last vertex Vn minus 2. So there's no worries about feasibility when we extend it by adding in the rightmost vertex V sub n. So to make sure you don't lose the forest for the trees, let me remind you what our high-level plan was. And let me point out that we actually just executed that plan quite successfully in this problem. The plan was to narrow down the candidates for what the optimal solution could be, to reason about the form of the optimal solution and argue that it has to look in a particular way. What did we just prove on the previous slide? We said that the optimal solution actually can only be one of 2 things. Either it excludes the final vertex, and it is nothing more than the max weight independent set from G prime, or if it includes the rightmost vertex, then it must be a maximum weight independent set from G double prime augmented with this last vertex V sub n. There's only 2 possibilities for what the optimal solution could possibly look like in terms of optimal solutions of smaller subproblems. So a corollary of this is that if a little birdie told us which case we were in, whether or not V sub n was in the optimal solution, we could just complete this by recursing on the appropriate subproblem. If the little birdie tells us the optimal solution doesn't have Vn, we just recurse on G prime. If the little birdie tells us V sub n is in the optimal solution, we recurse on G double prime and then add V sub n to the result. Now, of course, there is no little birdie, and we have no idea whether this rightmost vertex is in the optimal solution or not. But hey, there's only 2 possibilities, right? Here's an idea. Maybe it seems crazy, but why not try both possibilities and just return whichever one is better? Why do I suggest that maybe this is crazy? Well, if you stare at this and you think about it and you think about the ramifications of trying both possibilities as you recurse down the graph, this may start feeling a little bit like brute force search. And in fact it is. This is just a recursive organization of a brute force search. Nevertheless, as we'll see in the next video, if we're smart about eliminating redundancy, we can actually implement this idea in a linear time.